Okay, so we have been talking fluid statics all this while, which means we are talking about a fluid at rest, no velocity anywhere at any x, y, z location. The only thing that changes with space is the pressure, which in general is a function of x, y, z, but I guess we have been looking mainly at situations where it just varies, increases as you go deeper downward in z. What we are going to study now is fluid dynamics, which means we are looking at situations where there's motion and that causes stresses and forces in the fluid. So now we are looking at situations where the velocity fields in general are a function of space. U is u of x, y, z and time. V is v of x, y, z and time, and so on for w, except we'll probably ignore the third component. There's nothing gained by going 3D as opposed to 2D, and of course the pressure remains a function of space and time. So we have this, and we want to get an expression for how fluid motion, we want to get an equation that governs fluid motion in terms of this velocity field, and the only recourse we have as in any mechanics course is Newton's law. So what we want to do ultimately is write F equals ma and then relate these forces to the velocity field and so on with the acceleration as well. So that this whole equation now is an equation that relates stresses to fluid motion. And we'll make some assumptions. The simplest situations we can consider are good enough for illustrative purposes. So we'll start with some simplifying assumptions. We'll start with an inviscid flow. That means mu equals 0. For a lot of situations, this is a pretty decent approximation, even though we talked about viscosity being a primary property of fluids that gives rise to stresses. For a whole bunch of situations like high-speed flows, flows around aeroplanes, flows of water in large ducts, viscosity turns out to actually be not very influential. We'll also say that the density is more or less constant, so incompressible. We'll also look at steady flows, and lastly 2D flows are good enough, 3D doesn't really add any complexity. So we'll break this up into two parts. The first part we will look at the acceleration. So we'll try to figure out how is acceleration a function of the velocity vector, how do we define an acceleration for a fluid element. And once we have an expression for the acceleration, we'll go ahead and plug that into Newton's law, where we also have expressions for the forces. We need to first define the fluid particle's path, and the book sometimes says element, sometimes says parcel, fluid element, fluid parcel, fluid particle, all of these are interchangeable. What we're really talking about is a collection of matter whose motion we are analyzing and to which we want to apply Newton's law. So if we have a streamline, which is the steady path of particles, strictly speaking, a streamline is a curve that is tangential to the particle's path everywhere. And as the following video shows, it's fairly easy to define.
If we connect a DC voltage to a very fine wire, here 2 mils, and put the wire in the water, Electrolysis forms extremely small hydrogen bubbles which are swept off by the flow. Most of these bubbles are small enough so that they follow the flow quite accurately. A few large bubbles are also formed. We ignore them in observing the flow pattern. Here you see a probe with multiple thin fingers which makes many fine lines. Another kind of probe is a single wire with sections insulated so that we see bands of bubbles coming off the probe. In order to interpret flow pictures, we need to be quite clear about four concepts. These relate the pictures to the kinematic description of the flow field. The first concept is the path line. A path line is the trajectory or path of a given fluid element. Here we mark a small element with bubbles so that we can follow its path. If we took a time exposure, we would make the entire path visible. Instead, we superpose a path line, and you can check for yourself that each of these squares follows it. A streak line is a little different. It is the instantaneous locus or trace of all the fluid elements that pass through a given fixed point in space. If we run a short, uninsulated section of a bubble wire steadily, it shows us a streak line. In steady flow, each particle coming past the fixed point moves down the same path, and therefore the streak line is identical to the path line. We can check this by resuperposing the path line you saw earlier. The fourth concept we need is the streamline. A streamline is defined as any line that at a given instant is everywhere tangent to the velocity vectors of the flow field. The streamline is essentially a mathematical idea, and is very useful in many fluid flow analyses. But there's no way to make a streamline directly visible. You've seen that in steady flow, the path line and the streak line are the same, and you might suspect that the streamlines would coincide with them also. This is in fact the case. Consider a particle moving along in steady flow. As you saw, each particle moves down the same path line, so that it's always moving down this path towards the particle ahead of it. This means it is always tangent to the path, and that is how we defined a streamline. So in steady flow, the streamline, the streak line, and the path line are all the same, and we can use either streak lines or path lines to show us the streamline pattern.
And now that we have looked at what a streamline is, let's reanalyze that. So suppose I have a flow around a particle, around an object, and here's my fluid particle approaching. I could define at every point along the streamline, I could define a radius of curvature. I could define a streamwise coordinate s hat and a normal coordinate n hat. And what I want to do is now define my acceleration in terms of these coordinates. So once again, this r is the radius of curvature. Okay, s is my path along the streamline. And let's say v is my velocity vector, which is u I plus v j plus w k. The coordinate system I'm going to use is one in which x is in the plane of the paper, y is into it, and z is also in the plane of the paper. And we'll go back and forth between S, N, and X, Y, Z. So in streamwise coordinates, I would say that my acceleration vector A is given by the streamwise acceleration along S and the normal acceleration along N. And so the magnitude of the streamwise acceleration, if that's what I'm interested in, is the change in the particle velocity as a function of time along the streamwise coordinate. And so I could apply the chain rule and say this is del V del S times ds dt. And ds dt is nothing but V, because ds dt is the rate at which the particles covering distance along the streamline. So this I can rewrite now as a derivative of the velocity squared. So now that we have an acceleration in terms of the velocity, let's look at how we would apply this to a fluid element. Let's say the fluid element is rectangular, my streamline is going through that. So at the center of my fluid element, I have my coordinate system. And let's say the element has a depth delta y into the plane of the figure. So the dimensions of this fluid element are delta n in the normal direction, delta s along the streamline, and now what we are trying to do is apply Newton's law. So the forces in general are surface forces, which are in this case just pressure because we are ignoring viscous stresses. And there's the weight of the fluid element itself, which is a body force. Let's first look at force balance along the streamline. Force acting from the left would be delta P okay, we'll have to edit this. So if I do a force balance going from left to right, on the left hand side of the element, I have a force that's given by P minus delta P, where P is the pressure at the center line, and we assume that we have P plus delta P on the right hand side and P minus delta P on the left. So P minus delta P on the left acting towards the right times the area of the left face, which is delta n delta y. So this is the force on the left face acting in the right hand direction. We subtract the force acting on the right face acting in the left direction, which is P plus delta P times delta n delta y. So this is my surface force. My body force would be gamma times sine theta, where theta is the angle with the horizontal. So it's gamma times sine theta times the volume of the fluid element, which is delta n delta y delta s. So this expression that we have written out has both surface forces and body forces, and this whole thing needs to be equal to the mass, needs to be equal to the mass times acceleration. Now the mass is nothing but rho dv, so that's rho times delta n delta y delta s. And the acceleration that we just calculated was half times del v square by del s. If you were to simplify this by saying that delta p is del p del s times delta s, also noting that sin theta is dy ds, we would get something like gamma dy ds plus dp ds plus half rho so this is the general form of what is called the Bernoulli equation. We rarely use it in this form. We haven't yet assumed incompressible. We have just said rho is the local density. So we would simplify this further under the variable density assumption and write it in differential form in this fashion. And if we plug in rho is constant, we would get rho gz plus p plus rho v square by 2 is a constant, and this would follow by integrating this first equation on top. So this particular form is what we are going to use for most of this course. This is the Bernoulli equation, and what this is telling us is that if I have a fluid element, the velocity that it attains is the result of the local pressure field as well as the local hydrostatic pressure.